Hello, good morning. My name is Nathaniel Osgood. I'm director of the Computational Epidemiology Public Health Informatics Lab. And it's my great pleasure to be with you today to present a Bayesian machine learning leveraged method that integrates a dynamic model which characterizes theory associated with natural histories of COVID-19 and transmission of that pathogen, and integrates those with diverse updated time series, including wastewater time series critically when it's available, to provide this sort of unfolding picture of the underlying epidemiology in terms of the clinical situation and the public health situation. Now, this process basically renders a dynamic model, and it could be a wide variety of models, into an always updated service, and provides this way of understanding not just the current situation, but projecting that forward and asking what if questions. A key element by which you'll see that this works is by by considering multiple competing hypotheses as to the underlying state of the system at a given time, where those competing hypotheses jockey to best explain the data in a sort of survival of the fittest, with the most fit ones in terms of explaining the data surviving and those that are less fit dying out. And this induces a sort of estimate of the underlying distribution. Now, I'm going to provide more detail on this. And to do that, I'd like to switch over to my slides. So fundamentally here, this is a method for making sense of diverse time series, recognizing that, for example, when it comes to cases and tests, there's reciprocal interactions between them. Presenting individuals drive tests, and large number of tests, say, drive through sites, and contact tracing drive discovery of cases. And when we add wastewater to the mix, it adds yet more to our cacophony of data. Trying to square an understanding of what the wastewater signal is telling us with the epidemiology is often really challenging. And what we've provided here is a way for doing that leverages the powers of models for capturing theory, transmission models. And I'm going to be explaining in this talk, reflective of the diverse audience, some with very little experience or encounters with models, and some with a great deal. I'm going to try to provide a bit for each of them. So at a highest level view, what we're using is a machine learning approach, Bayesian machine learning, to combine transmission models with wastewater data and traditional data. This is far from a curve fitting approach. Instead, it's really inquiring into what's going on in the underlying situation. And more specifically, it seeks to identify this coherent understanding in terms of a picture of the underlying situation whose progression is consistent with logic of how COVID-19 progresses, the natural history of infection and how it transmits as captured by the transmission model. And it tries to understand that empirical data in that light and use it to best estimate the underlying situation. And this does involve inference from the observed data and where it's square with that theory. And once we've done that, we can project forward and ask what if questions. In many ways, this is similar to the idea of, with a weather model. To get the weather for tomorrow, we view a model as much more, the same model as much more reliable if it's been grounded with the data till this very evening than if you were using that same model as it predicted tomorrow's weather, say, from the beginning of the month. Same model, but it's constantly regrounded with data. And that's what adds a lot of capacity for its ability to effectively project. So here we're using this machine learning AI type method to integrate together a diverse set of time series, notably including wastewater data, to provide an estimate as to the current situation right now as articulated in terms of the model. And we use that then to project forward. This is an approach we've used with a dozen or so other conditions and pathogens, and which a growing number of others across the world are using. To the best of our knowledge, we're the first applying it to wastewater. So in a bit more detail, Bayesian machine learning combined with this dynamic model provides this way of updating our model state. We can apply it with most ODEs, most compartmental models very readily to produce this ongoing estimate of the underlying situation, the acute care state, including projection of them and asking what-if questions. We can exploit new wastewater data when it's available and otherwise fall back on traditional data alone. And it provides this computationally manageable way of integrating this data. And this approach is particularly easy to apply when we have separate wastewater and stormwater systems and systems with small transit times, but it can be readily extended to other such systems. And we're in the process of extending it for a wide variety of municipalities across Alberta, as well as extending it in various ways with the likelihood functions, et cetera. Now, at a technical level, we're leveraging two primary techniques here: particle filtering, which I'll be talking about in more detail, and particle MCMC, which is more sophisticated yet, and is yielding notable findings, but which I don't have time to cover in these 20 minutes. So a couple key facts about how particle filtering on its own, and as it's incorporated as a piece of particle MCMC works. So this is an approach which takes a stochastic underlying compartmental model, here a transmission model, and it runs it forward. But it runs it forward in a way that with each new observation, the understanding of the state of that model is corrected to align with the new data. And that process is performed recursively. When we get new data in, a new observation, say a new wastewater reading, we don't have to reconsider all previous ones. We just consider this new one and update the current estimate in light of that. Now, the way in which this does it, though, is very sophisticated. And for those who know about machine learning, you can almost consider it a type of ensemble method, if in a general sense of that term. So we're taking this model, which normally when we run it at any one time believes there's a certain number of people in each of these states and each of these compartments, and where the number in each compartment evolves over time according to the rules of the model. And instead, you could think of here extending this model out of the screen. So we have many layers of it, where each layer has a different hypothesis, nourishes a different hypothesis as to the underlying situation. We call each of those hypotheses a particle. And it has a complete hypothesis about the current situation right now. All the particles are at the same period of time. They each have different hypotheses, and they jockey to best explain the data. They compete to be consistent with the data. And here, not all particles are the same. Particles which have more credibility are associated with higher weights, and a weight of 2 compared to a weight of 1 indicates it's quite twice as frequent in the distribution. And there's the survival of the fittest, whereby particles that are more consistent with the data survive, those that are less consistent die out. So in a little bit more detail yet, we take this model and we subscript it by particles. And in our runs, we have 150,000 particles routinely for our production quality models if they're aggregate models and not regionally stratified, which would need more. And each particle has its own copy of the state. Between observations, those particles each run as a solitude going forward. But at observation points, there's a splaying that has to be done. There's an accounting that has to be done. We use a likelihood function to ask for a given particle, what's the likelihood it would explain this observed data? And that likelihood may be larger or maybe smaller. It's larger if it has a high likelihood of explaining that data, if it accords with that empirical data, and smaller if it's in variance with that, it just doesn't jive with that data. And we multiply the particle weights by this likelihood according to what's called the condensation algorithm. It goes by a slightly different name in computational statistics. So each particle is updated to sort of increase its credibility if it matches the data, and decrease it if it doesn't. They renormalize the weights. And then there's a resampling that goes on, whereby particles that are more consistent with the data have higher weights, multiply and are fruitful, but those that are not consistent with the data die out. I wish I had time to explain this, but basically each particle at a given time has a certain expectation. given that particles expectations say about how many cases there should be now or what the hospital census should be now, or when a new observation comes in, say here on the right, we compute its likelihood functions and we come up with a likelihood that particle state would explain this data. And by multiplying multiple likelihoods, we get a composite likelihood, and we use that to update the weights after normalize it and then renormalize. So when we have multiple measurands, we update the weights accordingly by multiplying these for our simple case. Now, to give you a sense, for example, a given sublikelihood function, one of these components of the overall one, might be formulated in a way that asks, what's the likelihood we would have seen this number of observed cases given this underlying situation in the model? And in this case, for example, we make use of a negative binomial distribution, comparing what the model expected versus what was actually seen empirically. Now, this talk is to a wastewater group, so I want to spend a lot of time talking about that component. And there's a component of this likelihood function that's a viral concentration sublikelihood, and that takes into account the data we get from our lab partners, whether in Saskatchewan or Alberta. Our work in Saskatoon makes use of data very kindly shared with us through John Giesi's lab through a collaboration. And we have almost entirely separate stormwater infrastructures with very short transit time, about 6 hours, stable temperatures, and it's particularly easy to integrate that data in. In the Alberta context, we're encountering a bigger variety of municipalities, and we may be doing some adjustments in older cities. I expect quite a bit of adjustment. So the likelihood function is going to be linking some representation of the shedding population scaled in a certain way and possibly delayed, smoothed, or temperature attenuated with the empirical concentration data. And we've considered 3 forms of likelihood functions, and thus far we found a log normal likelihood function for this most competitive. Gamma also does quite well. We found smoothing multiple measurements when they occur in the course of a week to actually increase the accuracy of our data, damping out some noise within the course of a week that we see. Here, we have a population within our transmission model, and some subset of that is a set of infectives. They're highlighted in reddish color here. And we need a characterization of the shedding population. We've considered one naively from the start, which is just a sum up of these compartments that are highlighted. But more generally, we have awaited some of them, reflecting the fact that people in earlier stages of infection are actually shedding more fecally, and hence more likely to be big contributors to the wastewater concentration signal for COVID-19, whereas those in later stages are less likely to be. And so we have different weights, and we've been working to try to best integrate elements from the literature with more refined shedding representations. We do find a weighted shedding representation, which heavily weights those in earlier stages of infection, reflecting the log linear, in other words, exponential decrease over time in COVID-19 viral load levels within a given person. We find those that really prioritize that to better match the data, better match the empirical data when we use them with the model. So we have this model, and each particle has a certain underlying state. It posits a certain number of people in each of these states. We have a shedding population that's implied by that. We have from that, possibly with delays, et cetera, a wastewater signal that we expect. And we compare that against the actual wastewater signal using a log normal or a gamma or what have you. So we're constantly using that to compare with wastewater where it's available. Where it's not, we just use a likelihood of 1 for that and continue on for that sub likelihood. I don't have time to go into capturing of delays, but we can capture it with delayings of that sort of weighted wastewater signal coming from the weighted shedding population. We can delay it before computing the wastewater signal for a given day. And there's ways to compute presence absence type measurements in addition to quantitation estimates using wastewater data. So what does all this come down to? I mean, why go through this whole rigmarole? Well, it has a lot of benefits. One is it gives you a sense of the underlying situation right now, just as many CAT scan images give you a 3D sense of the situation within a person, while each of those CAT scan images is very limited. So it is with all this data, including wastewater data, we can get kind of this 3D picture of the underlying epidemiological situation. And this includes estimates that we can compare with empirical data. Things here like number of suspected cases or wastewater concentrations. But critically, it includes a lot of latent factors. And really, this is why we have contracts from PHAC for each province, from FNIB, and from our health system, and why we report for Alberta as well, is to deal with these latent estimates. So, for example, the number of undiagnosed infectives, the effective reproductive number, taking into account, both cases that are observed and number of infections that are likely not observed. We can also critically project forward, and this is of key interest to a lot of our partners. For example, health system quantities like ICU census. We represent explicitly the ICU and its census at a given time, its number of people in it. We represent the non-ICU number of people in the hospital, and we can project those things forward after the time where we've estimated things to the current state. This is a transmission model, and we can run it forward for all the particles, this ensemble going forward, and examine what they anticipate in the next few weeks, for example, for the evolution of not just the things we observe, we can observe otherwise, but the things we can't. And this can include things like ICU and hospital population, hospital admissions, et cetera. Okay, so, in short here, combining machine learning and dynamic modeling, particle filtering, and in fact, particle MCMC even more powerfully, provides this convenient, versatile, and straightforward way of incorporating wastewater. And it turns out incorporation of wastewater, although I haven't shown it because of limits on time here, into our models improves their accuracy, improves their ability to match data till now, and improves the ability to project forward accurately. And it does so in a material way. So wastewater data matters, and smoothed wastewater data, smoothing within the course of a week can improve that yet further. Beyond providing a kind of probabilistic sense of the current underlying situation that utilizes that wastewater data understand all these latent quantities like number of undiagnosed infectives out there, number of new infections per day, force of infection, et cetera. We can use this to project forward and conduct what-if questions. And particle filtering use of wastewater data really can improve that projection accuracy. Wastewater data matters. It really can allow us to project forward better health system quantities as well as latent quantities. Wastewater data can be incorporated in a straightforward way by relating model estimates to the shedding population, possibly delayed, smoothed, attenuated for temperature to wastewater concentrations. And this does scale to handle episodic and presence absence wastewater measurements, in addition to quantitation. These results were facilitated in our initial work by straightforward infrastructure, including separate sewage systems, rapid transit times, auto sampling, et cetera, and lab correction associated with the N2 signal. But our work now is working to generalize that for other municipalities. And we're well aware of the fact that we need to do so, and we have model structures that we believe are responsive to that. This can be readily adapted to other dynamic models in municipalities. There's nothing privileging our dynamic models. And some municipal infrastructures may require substantial elaborations. Effective application of particle filtering does require here hundreds of thousands of particles to run simultaneously, which does require really substantive computational effort for reliable results. I'd like to thank all the students, our funders who have made this possible, and all who have inspired this work. Thank you so much, and I'm glad to answer questions.